Here comes a cat. Incoming cat. You wanted the teenage, middle-age angst.
There. You promised. You delivered.
Yeah. As written by some fucking dude that doesn't have a job. Maybe we should start putting that on YouTube Shorts.
I got songs for days, man. I got songs written for days.
So do I. There's one of them.
There you go.
There's ideas out of the head. I was going to show you. I don't know what we're doing today. I'm not doing linear algebra. Well, yes, we are. I like linear. First of all, if you're using the internet, you're using linear algebra. Dumb. Do you know how when you search yourself, Lorenzo, like I know you do every morning, do you know how does the internet know which page to give you and how is it ranking that? And what's the difference between a rating and a ranking?
That I do not know. It's eigenvalues all the way down.
It is eigenvalues all the way down. It's a hub and an authority rank. It's called page rank, which is awfully clever because the guy's last name is Page. But he called it the page rank. There's two. So you have the hub matrix, which is, I think, the source. Hyperlink, so the pages on the internet, which is a growing graph in time. So it's time dependent. It's not a stationary graph, which is interesting also, because usually you would use a finite stationary graph. It's going to be finite, but growing over time. But the pages are the nodes or vertices in the graph, and then the hyperlinks between them are the connections. And so when you do this, you're looking at, I don't know what the frick it is now. When I did my thesis 11 years ago, it was like 8 billion pages on the internet or something like this. So you have an 8 billion graph, and then you have to find the largest. If you have a strongly connected graph, there's a unique eigenvalue and eigenvector associated to this where the eigenvalue is positive and all the entries of the eigenvector are positive, and there's no other, and it's the unique linearly independent eigenvector associated to that eigenvalue by the Perron-Frobenius theorem, and all other eigenvectors associated to any other eigenvalue from this dominant, other than this dominant eigenvector and eigenvalue, have negative entries. So there's a unique way of doing it, because as soon as you have choice, you would ask, why wouldn't you use some other eigenvector? But if you have a strongly connected graph, I can create a irreducible matrix from this. The irreducible matrix will have a unique positive real eigenvalue with a positive eigenvector. How do I say positive for an eigenvector, which is a matrix which is in, or a vector which is in multi-dimensions? How do you order R2? Yeah.
algorithms that have been developed over the last 50 years to speed up computations for linear algebra on computer hardware.
I was gonna do something like that, and then I gave up on life a few years back, and so I wasn't gonna. But yes, I was gonna try and if you could tell Google how to speed up their algorithm by a day or two, they probably would give you some money. I should have done that. That didn't answer your question. I've been talking to a lot of bureaucrats lately, and then when you ask them something, they just dance around it and answer something else.
Well, that'll
But
kill your brain right there.
yeah, I know it's brain rot, but I am not sure. All I did was look at applying this to if you have. Here's okay. Let's tell that story of that in a dark room. I have say 3 cities. Unfortunately, the Western Canada doesn't really count. Maybe Vancouver, but you have Ottawa and Quebec and Toronto, and so you got 3 cities that Toronto. I'm keeping this 337. It goes over here with 314 and 666 because it was prime. And so here's 3 nodes. Let's call them 1 and 2 and 3. I believe this is backwards. Should I point this out? I'm talking to myself now, even though there's a camera. And I'm talking to Michael Lee. So Yi Lee or Michael Lee is my PhD supervisor. My question is basically extensions of his brain. I was explaining it to Noah the other day. And so what we would do is, what I was trying to do is get a graph like this, and it has to be directed. So let's do this. This is strongly connected now. What that intuitively means is from every node, I can find a directed path from every vertex to every other vertex. So if I want to go from 2 to 1, I have to go this way. If I want to go from 1 to 2, I can go that way. And obviously you can see that this is a directed 3 cycle. Or this is what we would call K3, which is isomorphic to C3, which is isomorphic to a couple other guys, but we'll leave it from there. So this is complete graphs, but they're directed now. And so now if these are the cities, would be the disease moving through this. So then we would have, say, let's call this, it's backwards, but for simplicity, I'll call it forwards. So we would call this beta 2-1 normally, because it would be, we're focused on who's getting infected, but I'll ignore this. So this is, I'm going from 1 to 2. That's easier for the brain, also for me on camera. This is a weight associated to this one would be 2, 3, and this one is the weight from 3 to 1. And then so I can create an associated weight matrix from this, which is going to have zeros on the diagonal. And then why are those not equidistant from each other? And then we can have, this is going to be beta 1, 2, 0. This one is beta 2, 3 or B2, 3. I still say beta even though I'm writing 3 because beta is the index for the mass action for infections of susceptible and infectious individuals is what we wanted to do. But you can apply this to a lot of other things, including hyperlinks on the internet. And then this is B31. And so we were trying to just take, if you had all the weights on there, if you had loops where you could infect yourself in your own city, which would make sense, especially the dirty Quebecers. Oh no, I don't know which one was Quebec. I think it was this one, or Montreal, and Toronto, and Ottawa. Okay, I'm not going to start doing that accent. And then you could have the other way. You were talking about the salmon going upstream, so you could also model this. The salmon coming down the stream, beta 1, 2 isn't going to be the same as beta 2, 1, et cetera, right? And so you can see now that I've complicated this and put all that on there, that would give you all non-zero entries in there. And then what we're asking is, can you find the eigenvector? Is there a largest eigenvector associated to this guy? So we would find the lambda. So now the lambda would be a lambda I minus b. The determinant of this is going to be the associated eigenvalues and then therefore eigenvectors from this. If it's strongly connected, and then long story short, what we wanted was you're going to get, I'm going to call it P for Perron Frobenius, and it's going to have 3 entries because it's 3-dimensional in this case. The internet is billions long, this eigenvector. And now what we wanted to ask was, you have to ask the right question. What is it not only, so first of all, the question 1 was in a dark room, which one of these is the largest value? Because that would say whichever thing that we're doing and we're cooking it up in here, and there's a little bit of, but then there's going to be ODE systems. at each one of these guys. So then di1 and then di2 dt and then di3 dt. And then there's going to be ODEs, systems of ODEs associated to this, where we're going to use the Kermack-McKendrick model of SIR, susceptible and infectious and recovered individuals. This is McKendrick, McGulick, which is it? Mac is Scottish and Mick is Irish. Yeah, Mick. That's the. Okay, I'll stop that. I hear a wop laughing in the background.
Hey, wait a second.
Wait a minute. Eye tie? You're like, that didn't make it better.
Well, hey,
Hey, Guido.
dear God. How many are there for us?
You said us Italians got a bunch of ways of saying something. Well, we got a bunch of ways of saying something too about you. Ah,
People.
sing, sing, sing. Okay, back to what I was talking about. So, long story short, I want to know actually not only which one of these is largest, but the rare question. I don't want to say why, because why is stupid usually in science. I don't know why the speed of light is 299,792,458 meters per second. I know how to calculate this and how the fact that it's a universal constant. So the why is usually unattainable. We want the hows. So how is it that this is, say, the largest guy? That would rank, so I would have a rating, and then I would rank him as the most important individual in this model, because this would say that in this city we have the most infected population. And then so when we have an endemic breakout like COVID or something like this, and we reach equilibrium, so it's not spreading through the system anymore, it's hit its maximum capacity, we want to know which of these cities is going to have the most infected individuals at any given point. So there's the first question. What is it? Which one of these guys? How is there a way of ranking this, and what are the different kinds of ratings and rankings that I could use to associate this? And this eigenvector process is extremely good because it takes into account not only your direct neighbors, but even if there was more of them. And this is what I'm doing in my thesis. If you have these guys and you had extremities funneling into Montreal and Ottawa and Toronto and all these different places, and then so we would have outlying cities into these megalopolis, then it turns out that it doesn't affect the ranking anymore. But this is not strongly connected anymore because you can't get from this one to this one. So we have to tweak this a little bit. The altered Perron Frobenius. I'll digress. So if we're doing this, what the other thing that we wanted to know was, the real question that we want to know is, what is it about the network that's picking? So say we get a system and we look at this, and I go back to what I started basically ignoring my PhD supervisor. That's how I came to my epiphany of getting somewhere. That was too much. We bit off far more than we could chew if I put all non-zero entries in there. It is definitely strongly connected because I can get all over the place. But what I'm trying to ask is, at first, is each of these guys depends on beta ij's. And so how are the eigenvector entries that you compute dependent as functions of the entries of the original matrix, which is something I had never thought about before until we started doing this question, which I've never really talked about out loud before either. But that's the question that I started asking myself. And man, is it complicated when you have a general, this guy. So what I wanted was, what's the simplest, strongest connected network I can get so that I have an irreducible matrix? And it's this. If you just take a directed cycle, it's strongly connected because I can now flow from everybody to everybody else. And therefore, this thing right here is an irreducible matrix. You can look up the irreducible matrix, not dibble, bull, irreducible matrix, which means you can't use a permutation matrix to multiply it on the left and the right to reorder it so that you get block zeros in it. There's no way to change this using permutations of the rows and columns so that you could reduce this into a smaller matrix and just ignore certain areas of the matrix, essentially, and therefore the network. So this is the the epiphany that I had in a dark room by myself, and then you're like, yay, and then who was interested? Michael Lee. And then now there's two of us that are interested. Yeah. And then back to the grind. Get in there and teach 1,800 classes in 2 years. And then we'll give you no credit for it and no full-time job. I'm not bitter. Yeah. Sour grapes. Oh, sour grapes is an Italian freaking parable, isn't it? It's there's a fox, danger sour grapes. Let me tell the sour grape story as I know it. There's a fox that wants the grapes in the tree, and all the squirrels and everybody else can climb, and they're getting their fill on the grapes. But every time he tries, he jumps and he can't climb the tree, and he can't jump high enough to get the grapes. So he's like, I didn't really want the grapes anyways. But then he starts eating all the other animals. Mm, yeah, so danger.
Is that an Aesop parable?
I don't know. I can't remember. I was just watching it. Yeah. And then it came to my mind when I was watching the Sasquatch Gang, a movie about this. And there's a big giant, can I say fat still? Big giant fat guy I just did twice. And he wants this girlfriend, but then she doesn't want him. He's going to go with the other guy. So he's like, there's only one thing left to do, sour grapes. And then he goes and, yeah, makes up the fact that there's a Sasquatch, and they're trying to pretend that there's a Sasquatch in the town. It's a pretty funny show. You'd like it. Anyways, sour grapes. So, Michael and I now realize that I can, for all intents and purposes, maybe I should try and flesh that out and see if I could do it still. Let's see if I still got the riz. Okay, that was different. When I old man screamed like that, I pulled my arm, freaking this muscle right here somewhere in there. I don't know which one that is. But loading a double bass into the thing, and then I still have that rib that hurts. So now I can't erase the board with either of my arms. Pain is weakness leaving the body. So this is a strongly connected network, which means intuitively I can get a directed path from every vertex to every other vertex. What that will do is give you, if and only if, an irreducible matrix. And then if you have an irreducible matrix, the Perron-Frobenius theorem says there exists a unique eigenvector which is real inside the complex numbers, so I don't have to worry about taking the complex conjugate or doing any of these types of things, which has its spectral radius equal to the absolute value of this. It will be positive. It's also positive. That's okay. This will be positive real number, which is associated to this, which is good. And it is the spectral radius, the spectral radius is the maximum of all the complex moduli of these guys, such that the complex variable is in the spectrum, the different spectrum, the spectrum of the matrix. The spectrum is in a finite dimensional operator. The spectrum is just the eigenvalues. If you want to see the where is this? No, I don't know where it is. I don't know where the book is anymore. There's a generalization of spectrum. We won't get into that either. So now I have this, and associated to that, there is only one. There can be only one eigenvector. I'm going to call it P lambda, associated to this positive real eigenvector, and it's greater than 0 is what I'm saying. What that means intuitively is that all the entries are positive. There's no 0 entries and there's no negative entries in that eigenvector. And so what I want to know is, can we play that game now? I want to find this vector and have it be positive, and it will depend on all of these guys. And then I want to rank and get conditions on when I could guarantee that the first entry in that eigenvector will be larger than all the other ones. This is what I spent a lot of time doing in a dark room. Fucking, it won't erase. The one time I have a hard time erasing, it won't erase properly. So now what I want, let's do this. I have lambda I, no, lambda, I said lambda I minus b is going to be what? Lambda negative b120, 0 lambda negative b23, negative b310 lambda. Then I want the determinant of that. How do you turn it into a determinant? Get rid of the little ticky things. There, now it's a determinant. What are we going to do? I'm going to cofactor expand along this top row and just be nice, and we're going to try and factor this. So we'll find the largest positive eigenvalue and then the eigenvector from this guy. This is going to be non-trivial. I don't remember how to do it. It's been a while. Also, this is a good lesson when you go to Mars or these types of things. Complicated tasks fall off within about 4 months. So if I see you in half a year, none of you will remember how to do eigenvalues or eigenvectors, let alone what I'm trying to do with this ranking business to find the spread of infectious diseases inside a given population.
The moral of the story is practice for reinforcement.
Practice makes perfection. Practice makes perfection. That was the moral. Shut up back there in the peanut gallery. You're correct, but never interrupt me again. That's the other one. Zing. Okay, I'm just killing time because I don't remember how to cofactor expand. I'm trying to do it in my head as I blab. So thank you for interrupting. Let's do this. So what is this? This is A11 C11 plus A12 C12 plus A13 C13. I regurgitated this because my kid's in linear algebra. See, I'm doing this in a much more sophisticated problem, but practice makes perfect, and I've just regurgitated cofactor expansion along the top row. That's going to be now what? This one I don't give a shit about because it's 0. I can say that on here. No, we're trying to monetize. I'm going to say poop from now on. Poops and tickles. Poops and tickles. It's shits and giggles, but then, so I started saying poops and tickles with patent pending, patent pending, patent pending. So I don't need to do this one. Okay, first of all, this is A13, C13. And then cofactors, I say, are signed minor. So this is A11, M11, because this cofactor is the same. 1 plus 2 is odd, though, so this will be minus A12, M12, plus A13, M13. Cofactors and minors are the same up to their sign. This one will be the same. This one will be the same because 1 plus 3 is 4, and 1 to the negative 1 to the 4 is going to be 1. 1 plus 3 is going to be odd, so negative 1 to the odd. Cij is negative 1 to the I plus j, mij. All right. Now what do I need? Now in that minor, I don't have to compute this guy because I have 0 times it. But now what is this one? This one is lambda times. You should have seen what it looked like when I was doing all non-zero entries. It was a freaking, and this is 3 by 3. Try doing it for a billion by a billion. Yeah, it takes Google a few days to compute this thing. My toe just busted out of my sock. Can I show everybody? It's bothering me. I'm not stopping, but I just thought I'd share. This is how you do science. I don't care. Keep going. This is going to be M11 is obtained by blocking off row 1 and column 1. Lambda negative B12. Do you see what we're going to get? Oh, it's going to go away just a second. Minus A12 is negative B12. So we're going to get positive in there because there should be no negatives because it said the eigenvalues are going to be positive. And then what do we have? We have obtained by bliss and this and this, bliss and bliss. Oh, so do you see what we got? We got a monic polynomial, which is only going to have the determinant. The determinant is the last constant coefficient, if you know these results also. These are useful results. I'll show you what minors are, but you don't know what principal minors are. But the characteristic polynomial of a matrix is equal to lambda to the n minus the trace of a lambda to the n minus 1 plus dot 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 plus all the other coefficients or sums of principal minors times negative 1 to the n times the determinant of a. So when I'm already seeing it now. So this is going to be 0, 0. Yeah, that's a lot of negatives. But I'm going to have negative B31, negative B23. And now do you see what that's going to be? I can canoe. So this is lambda cubed because this one's 0. And then this is plus B12. And then what do I get? Minus, minus are going to cancel, but then I get minus negative B3, 1 and B2, 3. So this is equal to lambda cubed minus, which is the geometric average. This way, this is B1, 2, B2, 3, B3, 1. And if you're strongly connected, you can always write them so that you can write this indexing so that you get the 1 to 2, the 2 to the 2 to the 2 to the 3, and then the 3's connected and the 1's loop back around, which is describing this loop right here. There's a lot of stuff going on right now. I'll give you a small window in my head. What that says is, oh, can you do this now? Can you find the other two? I should make you do that. Lorenzo. Tim, you're going to do it too. I'm not going to let you off. But now what that says is lambda cubed minus B1, 2, B2, 3, B3, 1 is, I want to know when this is equal to 0.
Oh, you use a factor that, right?
Right. So the first one is going to be lambda. The positive eigenvalue is going to be the third root of B1, 2, B2, 3, B3, 1. But now that I know that that's a root, you can use long division and get a quadratic, and then the quadratic equation will give you you're in business. It looks horrible. Just because I can do it doesn't mean I should. And Einstein says I can do anything almost mathematically, but it's so complicated it'll be rendered useless. All I need is this one. This is the spectral radius, and it is the geometric mean, which is the nth root of all the products of the three guys in there. Now do you see what I have to do? I have to put that back into the lambda b minus a and find the eigenvector associated to that guy. I want it to be dependent on those guys, and then I want to rank and give conditions on when that will be the first entry in the eigenvector. So let's look at the eigenvector associated to this guy. The eigenvector associated to me has to be the determinant of, this is the lambda. I'm going to call it, let's call this guy, what do we want to call that? Just a number?
Be unique and say beta.
Beta. Okay. So this is beta to the 1/3. The guy on the inside. So then we have, and then what did I have? It was negative B12, 0, 0, beta to the 1/3, 0, no, B, negative B23, and then negative B31, 0, beta to the 1/3. Now do you have to, what I'm doing is I'm trying to find the null space of lambda b minus a is what the linearly independent vectors are going to span the null space of this guy. So really what I'm looking for is P1, P2, P3 equals 0 now. And I want to solve this homogeneous system. So ignoring the p's now again, this is the augmented, what do you do when you solve a linear system? Everybody from linear algebra that's actually watching, we're solving this augmented matrix now, which is homogeneous. Can you row reduce this? And how do you know this? A really good hint for everybody in the room and not in the room is when you're doing this and it gets all of a sudden a whole hot mess complicated, the baby eigenvalue eigenvector problems they were giving you in the first year linear algebra class were just so that you could get the process. But the moral of the story here is this is an eigenvector or an eigenvalue if and only if the determinant is 0, which means one of the rows has to disappear. You could just kill one of the rows. That's a good tip. I've got a couple other tips for you. But for late, but one of the rows has to go away to 0. So we have to. But what should I do? I also know that beta to the 1/3 is not 0, right? Okay, yeah, I'm checking. Yeah, Lorenzo's following. Tim's just being quiet. Did you follow? Did you not? Did you nod off? Are you nodding off? Is he playing with his phone? Stop that! Or are you interested and mesmerized?
I was actually on the Wikipedia rabbit hole about eigenbasis, so.
Yes, yeah. I'm spinning. I spent 6 years in a dark room doing this, so I might be ahead of you guys a little bit. Yeah. So I'm going to divide by this guy to get myself a leading one. So row 1 goes to negative beta 1/3 row 1, which is going to give me 0, negative beta 1, 2 over beta to the 1/3. 0. You see why I called it beta, so I didn't have to carry around that junk. This is also when you have, remember, beta to the 1/3 is B12, B23, B31 to the 1/3. I don't want to carry that around the whole time in this row reduction on top of how horrible it is.
That first entry should be a 1, right?
Yeah. My hand doesn't even listen to my mouth. Nobody does. All right, and then I have 0, beta 1/3. You can correct me in the comments. Please comment. You're an idiot. Still, I'll take that too. I'll take that one. That was a 1 also. And then this is beta B31, 0, beta to the 1/3. Now, why did I do that? Because now it's a lot easier to take this guy, and what are we going to get in the first entry? We're going to get a 1 most likely. But now I can say row 3 goes to row 3 minus or plus beta 31 row 1, which will give me 1 negative B12 over beta 1/3, 0, 0. These zeros don't change, which is good for a homogeneous system at least. And then now, what do I have? I didn't change this one, beta 1/3, negative B23. And now I'm doing this, I'm multiplying this by positive B31. That's why I did it. So I'm going to get 0 there. That's why I did it. Do you see the mantra also helps when this is much more complicated? My toe's sticking out of my sock and it's bothering me. Every time I wiggle my foot, it's like, yeah, I'm loose. No, you're not. Get back in there. I'm escaped again. Throw this sock away. Someone want to sew my socks? I need socks. I'm going to go fund me. I can't afford socks even anymore. God damn it. I really hope I get that extended sessional. The haters listening. Then now what are we doing? I'm multiplying by plus and I'm adding it, but I have a 0 here, so that's good. So then what am I going to get? It won't change it too much. So then I'm going to get negative beta 1/2, beta 3/1 over beta to the 1/3. And then this is just going to be beta to the 1/3 still, because it's this plus 0. That's not so bad. Now in this row, do you see, I should have done it ahead of time, but I'm going to do row 2 goes to negative beta 1/3, row 2. And I'm just going to do it here. I'm going to get a 1 and then beta to the 1/3. Beta. Old man noise. Why did I do that? Because now I have 2 leading 1s and then I have to eliminate below. So row 3 is going to go to positive beta 1/2, beta 3/1 over B. I'm calling them betas. They're all betas. They're all betas to me. Times row 2. And that's going to give me a headache among other things. You can see when I say this, beta 1/3, 0, 0, 0, 0 won't change. This isn't going to change. 1 beta 2/3, beta 1/3. Michael's like, just go figure it out. I hate you. I like math though, so let's go do this. Oh, we're on the home stretch. We're almost there. We're almost in REF. So this minus this. So I'm multiplying this one by beta 1/2, beta 3/1 over beta to the 1/3, which is going to give me, we're multiplying by this, so that's going to give me 0. That's why I did it. And now we got what? Squared. Now I've got, yes. No, wait. What are we doing? We're doing this multiplied by this, so I have negative beta 1/2, beta 2/3, beta B3/1 over beta. So beta to the 2/3. Oh crap, minus that guy. I'm adding, yeah, so plus this guy, beta to the 1/3.
So now because that's beta to the 2/3 in the denominator and beta cubed in the numerator,
Yeah.
you get beta to the 1/3 plus a negative beta to the 1/3, so you get a 0. There's that 0 you were talking about.
I was gonna go there, but what Lorenzo said. So what he's, yeah. What did I tell you about interrupting me? Yeah, okay. I said you were right the first time too. I said never do it again. So what he's doing, he came to the same conclusion that there had to be a 0, but then I was doing all the work anyways. I'd already catfished you. So yes, this is 0. Yay, that whole calculation is 0. There had to be a row of zeros, which is good.
Ah, God, that makes me so happy, actually.
You're following along. Yeah, math is hard, but not fun math is not an oxymoron. I keep telling people I can't take the hardness out of it. Get hard, stay hard. But three fingers in the honeycomb. What? I was thinking about Red Hot Chili Peppers. Red Hot Chili Peppers. What was I doing? I'm easy. Yeah. 3 fingers at a time. So now what does this say? This says now that who's the free variable? The column that doesn't have the leading entry. So now we can say P3 is free. And that says, see the negative is going to be positive. So this says P2 is equal to positive B23 over beta to the 1/3, which is, we could just call it our spectral radius too. This is rho. The whole time I could have called it rho. And P1 is equal to B12 over rho, the spectral radius, because that was the spectral radius. Remember, beta to the 1/3 is the largest eigenvalue, which will be the spectral radius of this, which is unique and positive and real. So now this gives us the eigenvector, which is, there's a unique one, which is the span of this guy, which says that he's invariant under linear transformation of this matrix, but that's a different story. So this says our unique eigenvector associated to this guy with the help of Lorenzo. I had quite honestly forgot. I had catfished myself, if I'm being honest. And I forgot that was going to turn into a 0. I'm like, fuck, I'm going to have to calculate that. But Lorenzo was ahead of me. So good. He's just going to take over. I don't even need to do this anymore. So this is what? Yeah, 1. And then what we're going to do is, this is going to be P1 is beta 2, or sorry, B23 over rho, and this will be B12 over rho times t. But up to t, this is the unique eigenvector, which it has all positive entries, which is associated to the unique eigenvector, which is the spectral radius of this guy, which we call rho usually, which was the 3rd root of B12, B23, B31. And then a student came up the other day in class and said, I had an engineer instructor, and they said, if you don't put this on there, I'm going to take a mark off if you didn't put the little hook on there. And I was like, how dare he? And then you know what made me laugh? I took out my calculator. I was like, let's see what the calculator has. And you know what the calculator doesn't have? The little hook. 2 did. Oh, look, there's no little hook. Ba-ba-ba.
Do you want to tell them the secret that engineering just uses math to weed out engineers?
Yeah. So then the history of it was just, this was the Greeks, and then they had to put the mantissa on top, and then they were like, and then there's the evolution of that. So here's mathematicians, because we know what we're doing. Here's physicists, and then here's engineers who don't know what the hell they're doing. So don't listen to engineers, listen to mathematicians, dumbass. Zing, zing, zing. I want to find out who it was, or he or she. It could have been a girl teaching it. I want to assume that it was a boy. She said he, but that makes me laugh. So now we're not done. How can I get conditions to guarantee that this is the largest? It's fairly easy. And it looks much. This was when I only remember. This was the simplest strongly connected network I could think of, was the directed cycle, 3 cycle. And so if I want P3 to be the largest, then that was Tirana. Toronto gosh. So if I want this or that guy to be the largest, and therefore the most important, this is also how, if you want to get into this in interesting things and you get on either side of the spectrum, these ideologues that don't like you swearing or don't like you searching for certain things, they know how to, they don't know how, but they have an engineer that would know how, and he doesn't really know how, and he's referenced and outsourced and then given zero credit to a mathematician that knows how to rank this, and then you can pad the weights of this so that it will no longer be the largest, and then when you search for it, it won't come up on the first page, it'll come up on like page 300. It's there still, but out of the billions, who searches past page 1 when you search for something? I do, because I learned how the algorithm works. Page 2 and 3 usually gives you better results, also a good tip. A lot of the time, especially when they're trying to have you not search for the thing that you want, like moviesjoy.is, won't come. Search it right now. It won't come up on page 1. It'll come up on page like 2 or 3. What I've noticed. Anyways, for this to be the largest guy, P3 is equal to 1. So if I want that to be the largest, all I need is P2 to be less than 1 and P3 to be less than 1. And now I have conditions on my eigenvalues and the entries of this matrix for which I would get the largest eigenvalue and eigenvector. On top of it, it gets worse from there, because now that was just the associated weight matrix. But now, like I said, and you'd already forgot, I already have differential equations also on this at each one. And these are nonlinear differential equations. And so what is it? Say I fix this network, but then I change from infectious diseases to modeling how predator-preys cooperate, or how, say, Lorenzo, that bears would turn into a hybrid bear. What the most important condition would be is, what's the most important would be, where's the most in hybrid bears occurring in which landmass? And now we have this connection, and what is it? So now what we're asking is, if I fix the network, what is it about the dynamics that will pick this to be the largest? And if I fix the dynamics, what is it when I change the network, which Yep, I was confused about something. I lost the cap to my marker. Are we on now? Check, check, check. Very true. And simplexes, simplicial complexes. This is a 1 simplex, this is a 2 simplex, this is a 3 simplex. This is a 0 simplex. Is that what we're talking about? It's your handle. Pachinko. Oh, we're going to Russian in here? Probably, yes, then. That was stereotyping, but yes, smarty pants. Anyways, let's end on me being able to catch two pens at the same time. Well, I did it the first time. So there's roughly what I did, among other things, in a dark room for a lot of years, while I independently, with almost no help from that B word, raised my daughter. So I got a master's degree and a PhD in a dark room, and then had to go home and raise my toddler at the same time. She was born in 2008, and I started the master's degree in 2007. So and I got the master's degree in 2009, and then I got the PhD in 2015. But you can apply this to coupled networks. If you have a machine and three things are connected to each other and then they're vibrating, you can find out where the vibrations are going to accumulate in this. And you can do this for coupled oscillators also in engineering, freaking engineers. And then you can do this for the spread or species competitions. And you can flip this ranking on its head. In this one, I want to know where the most infected individuals are. But if you flip the ranking on its head and look for the lowest, that's the species that's going to go extinct soon. We'll do this with we'll do this with the bears. Anyways, I'm tired and I have to go do, for lack of a better phrase, adulting. I'm out.